Hi, everyone, and welcome to The Explainer. I am absolutely thrilled to have you here today because, well, we're tackling one of the most notoriously intimidating challenges in all of tech, the system design interview. Our goal today is simple, but honestly, it's pretty powerful. We're going to completely dismantle the myth that system design is just about memorizing a bunch of complex canonical diagrams. If you've ever felt totally lost staring at a blank whiteboard, or kind of wondered how you're supposed to bridge the gap between super abstract requirements and a rock-solid concrete architecture, you are in exactly the right place. So, let's get started.
Okay, let's dive into this. I want to shatter some expectations right out of the gate with this quote. It feels completely counterintuitive, doesn't it? You spend weeks studying dozens of architectures, you memorize exactly how to draw out a massive global video sharing platform, and then you get rejected. Well, strong engineers fail system design interviews every single day. And it's not because their final diagram was necessarily wrong, it's because they optimized for the entirely wrong signals.
So why exactly does this happen? Why do genuinely great engineers fail? It's basically because candidates often rush to draw those memorized textbook diagrams without ever actually clarifying the constraints of the problem. They treat crucial building blocks, things like caches, queues, databases, as these opaque little primitives. They'll just drop a Kafka box on the whiteboard to magically fix a bottleneck without really understanding the actual mechanics, the trade-offs, or critically, what happens when that component inevitably fails under pressure. Remember, interviewers aren't testing your memory, they are testing your real-time architectural judgment.
To help fix this, here's our roadmap for today's explainer. We're going to cover the system design trap, mastering BOTEC estimations, the latency spectrum, abstracting system complexity, and finally, the interview success framework. We'll be moving straight from theoretical math right into practical interview application.
Section 1, the system design trap. Let's diagnose the core problem with engineering interviews. So, the ultimate antidote to this whole design trap is something called BOTEC, or back-of-the-envelope calculations. Think of a BOTEC like an urban planner trying to estimate a city's population. Instead of going around knocking on literally every single door for an exact census, they just count the houses in one neighborhood and multiply that by the average household size. It's fast, and hey, it's directionally correct. In system design, BOTECs allow us to abstract away all that overwhelming, messy data center complexity into basic server types and manageable math. It lets us prove our architecture is actually feasible before we even draw a single box. Moving on to Section 2, Mastering BOTEC Estimations. Here is how we abstract away the overwhelming complexity of modern infrastructure. And this brilliantly illustrates how we can classify commodity hardware in modern data centers to easily estimate our resource requirements without having to model a million different variables. Really, we just need to understand these three primary server types. First up, the web server. This guy handles your API calls and concurrent connections. It doesn't need massive storage, but it definitely needs solid processing power. Second, we have the application server. This is where your heavy business logic lives, so it requires massive CPU and RAM. And third, the storage server. This one is optimized for high-density data retention, covering everything from blob storage for massive video files to your standard RDBMS for user metadata. Understanding these three basic profiles is absolutely the secret to scaling cost-effectively. Section 3, the latency spectrum. Let's talk about instilling true machine sympathy. Just look at this number for a second. 150 million nanoseconds. That is the staggering amount of time it takes for a global network packet to make a round trip from California to the Netherlands and back. When you're out there designing a system, the speed of light is a very real physical boundary you have to deal with. But let's be honest, nanoseconds are incredibly hard for the human brain to really comprehend. Now, what's really interesting about this slide is how we can translate that dry nanosecond data into human time comparisons. It reveals something totally fascinating. Think about it. If an L1 cache reference, which is the absolute fastest operation on a CPU, equals just one quick heartbeat, then grabbing data from main memory is kind of like taking the time to brush your teeth. Making a round trip within the exact same data center, that feels like a 5.8-day vacation. And that packet we talked about traveling across the globe, that takes the equivalent of 4.8 years. I mean, that's an entire bachelor's degree. This right here is exactly why remote database calls are so ridiculously expensive, and it's why we rely so heavily on things like edge caching and CDNs. Section 4, Abstracting System Complexity. How to categorize workloads based on physical latency constraints. So, how do we take all this knowledge about physical hardware and actually apply it to the requests hitting our systems? Well, we do it by breaking down real workloads into three main categories, which helps us quickly spot bottlenecks. First, we have CPU-bound requests. These are bottlenecks by pure processing speed. Think of things like compressing a big file. Next up are memory-bound requests, which are limited by your memory subsystem, like reading sequentially from RAM. Finally, we have I/O-bound requests, limited by the disk or the network subsystem. Actually, most scaling issues you'll face in system design interviews revolve heavily around I/O-bound requests. Why? Because, as we just saw with our humanized latency table, hitting a mechanical disk or a remote network is excruciatingly slow. Now, to make this super interview-friendly, we use the order of magnitude rule of thumb. And, the best part, you absolutely do not need a calculator for this. Just remember, if a CPU task takes X amount of time, a memory task is going to take roughly 10 times longer. An I/O task, that'll take 100 times longer. By just memorizing this incredibly simple relationship, you can instantly prove to an interviewer exactly why a specific workload needs to be shifted from an agonizing I/O-bound database call right into a lightning-fast memory-bound Redis cache. Let's move to and see how this builds into an actual real-world calculation of system throughput. Let's say you've got a system with 100 million daily active users, and let's assume each user makes about 5 requests. Okay, so that's 500 million daily requests total. Now, technically, there are exactly 86,400 seconds in a day. But hey, for a quick whiteboard BOTC, we just round that up to a nice, clean 100,000 seconds. So 500 million divided by 100,000 immediately gives us an average of 5,000 requests per second. But remember, systems have to survive sudden traffic spikes, so we multiply that average by a factor of 2 to 5, which gives us a peak load target of anywhere from 10,000 to 25,000 RPS. Boom! Just like that, you have mathematically justified exactly how many web servers you need to provision. Section 5, the Interview Success Framework. Time to bring all this math and theory straight back into the application phase.
So the crucial point is this behavioral framework. You absolutely must move through a reasoning loop instead of just locking onto a single rigid diagram. First step, clarify the constraints. Take a super vague prompt like design Twitter and turn it into hard functional and non-functional numbers. Second step, explicitly state your assumptions out loud. Third, and honestly most importantly, find the breaking point. Look your interviewer in the eye and say, hey, this architecture works great for our current load, but if read traffic doubles next month, this database is going to become a massive I/O bottleneck, and we'll definitely need to introduce sharding. You've got to treat your architecture as a living hypothesis, not just a final static destination.
Ultimately, the strongest candidates treat the interview as a collaborative design review. If the interviewer suddenly changes the constraints midstream, they don't get defensive at all. Instead, they calmly use their BOTEC skills and that latency knowledge we just talked about to smoothly pivot the design. Remember, they're really just evaluating whether they'd want to work alongside you during a messy, ambiguous production incident at 2 a.m. So I want to leave you with this provocative thought to carry into your very next whiteboard session. If you stop trying to prove that you perfectly memorize the quote-unquote right answer, and instead genuinely treat your interviewer like a teammate, what kind of incredible systems will you build together? Thanks so much for joining me on The Explainer today, and keep learning.